Okay, let's discuss sampling distributions. And we will be introducing the central limit theorem, which is a huge theorem that we'll be using from now until the end of the semester. So, introduction to sampling distributions. The sampling distribution of a statistic such as the sample mean or sample proportion is the probability distribution of all values of the statistic when all possible samples of size n are taken from the population. That makes absolutely no sense, and that's fine. By the end of this video, that should hopefully become more clear of what we are talking about. The point estimator is a single valued estimate calculated from the sample data, which is intended to be close to the true population value. Essentially, whenever we're calculating x bar or s squared, so our mean, our standard deviation, or our variance, we are estimating or we're trying to make predictions about what we would know about the population based on those statistics that we calculated from a randomly selected sample. Now, let's discuss a very specific distribution using the central limit theorem. So if the average value of an estimator equals the population parameter being estimated, the estimated is said to be unbiased. The sample median is an unbiased estimator of the population median if the distribution of the population is symmetric, because we know if the population is symmetric, then the mean and the median are equal and in the center. Unbiased versus biased estimators. So here's a visual of understanding what it means to be biased versus unbiased. Notice the spread of the estimators amongst the target. And the difference in the bias area is that they're grouped together. They are not spread out amongst the entire population. And that creates a biased sample, and therefore biased estimators, because you're calculating those estimators from the sample data. Now, unbiased estimators is the sample mean, as long as it's taken from a randomly selected sample. The sample proportion is p hat. Okay, so p with a little, literally looks like it has a party hat on. And the sample variance s squared. It can be shown that for a population of infinite size, the variance of the mean, sigma squared sub x bar, equals the following formula, while the standard deviation is sigma over the square root of n, because you know the difference between variance and standard deviation is simply a square root. Now, these calculations here, the standard deviation, which is called the standard error of the mean, is referencing when we are talking about taking samples out of the population. So more than one, actually every sample that can be taken and created of a certain size n. We refer to this sigma sub x bar as the standard error of the mean, as I mentioned, generally called the standard error, which is the standard deviation for that point estimator. Now, we also have a standard error for proportions as well. We're just not going to explore that in this lecture. We will use the standard error of the mean to indicate how far the sample mean is from the population mean. So one of the biggest differences that we're going to notice between the probabilities, the continuous probabilities that we've been calculating and the ones that we are about to calculate, is the fact that we now have more than one person that we're talking about. So before it was calculating the probability that a student A has a higher GPA than 3.5. Okay, that would be a straightforward continuous probability. But if I said, what is the probability that all the students in Professor Wiggins' stat class has a GPA higher than 3.5? Now we are talking about a group of people, and that would require the central limit theorem and the standard error formula. When we apply the central limit theorem, we assume that the population has an infinite number of members. mainly because we usually don't know that much about the population and exactly how big it is. When we sample the replacement, the population becomes essentially infinite. If you think about it, if I replace people back into the population after they've been selected, then that's going to create an infinite cycle of people to choose from. However, in reality, there are applications that involve sampling without replacement, and therefore these populations are very specifically finite, and adjustment needs to be made to that standard error. So that adjustment is the size of the population minus the size of the sample divided by the size of the population minus 1. So there's the proportion factor that we need to multiply by when we know that the population is finite. And again, if we know it's finite, then we should know the size, n. The finite population correction factor should be used if n is greater than 5% of the finite population size. So if we see that n is too small, well, we already know that that's an issue in general. Typically, if n is less than or equal to, just strictly less than 30, then the sample size is not large enough. And we would need to know a lot more about that population in order to make valid conclusions. The central limit theorem is a very important theorem which summarizes the distribution of the sample mean. The distribution of the sample mean becomes closer to a normal distribution as the sample size becomes larger, regardless of the shape of the population for which the sample is drawn. So one thing that we are going to see is before, when the population was not normally distributed, we did struggle with what do we do next if we don't have a symmetrical normally distributed curve. But now what we're talking about is the fact that the central limit theorem is proven to create a perfectly standard normal curve when done properly. So if I am looking at a population, okay, so let's say that this is all Northwestern students. Okay, so we have student 1, student 2, student 3, a bunch of people, a bunch of X's, which stand for students. And I say, okay, the shape of the population is not normally distributed. It's like the Rocky Mountains, right? And we're talking about these students' GPAs. Okay, so if we plotted those out, let's say they are not symmetrically distributed. And we are looking to create a perfectly standard normal curve so that we can take the probability of a group of 100 students having a GPA higher than 3.5. So I've chosen the sample size. The sample size is 100. And the way the central limit theorem is working, or the way that a sampling distribution works, is you dive into this population and randomly select 100 students and calculate the average GPA of that first sample. And then you do it again. Randomly select 100 students and calculate an average GPA. And you continue that process. Now, when we were talking about with replacement, what that meant is this first 100 students, after you calculated their average GPA, you put them back in the population. And then when you randomly selected the second sample, it's possible that some of the same students from the first sample may be reselected in the second sample. And this continues, and we never run out of students to choose from because we are replacing them, which is why we would consider the population size infinite. And we don't need the correction factor. If we did not replace, let's say we had 1,000 students in the population and we were collecting samples of 100, which means we'd have 10 samples drawn of uniquely individual students in those samples, then we'd have to use that correction factor in order to account for the fact that our sample size is greater than 5% of the overall population and we did not replace students back, making it finite. Now, after we collect all of these X bars, what happens next is they become the data values in the new curve. So this original curve is of individual student GPAs. So here's all my individual student GPAs. But when we created these X bars, now those are the data values that create the distribution. And the averages, the distribution of averages, will always be perfectly symmetric normal curve. Okay, where the mean of the original distribution, mu, standard deviation of the original distribution, sigma, the mean of our means, essentially we're taking the average of averages, that is always going to be the same as the mean of the original population, so the center does not change. But the standard error of the averages, you would take the standard deviation of the population that all of these calculations came from and divide by the square root of the sample size in order to get the standard error of this sampling distribution. If sufficiently large random sample, like bigger than 30, is drawn from a population with mean mu and standard deviation sigma, as I just mentioned, the average of the averages is the same as the average of the individual GPAs, individual characteristics or data values. And the standard error is calculated by sigma over the square root of n. So really the only difference that we're going to see when we are using our guru to calculate probabilities using the central limit theorem is we will have to calculate sigma divided by the square root of n to put it in for that standard deviation part. Now, this shows that if the original population was bimodal, after we create the sampling distribution, it will be a standard normal or a very normal curve, much more narrow and normal. Exponential distribution also creates a normal. Literally, any distribution will be a skinny normal curve using a sampling distribution, even one that was already normally distributed. Now it's just more normally distributed, more normal, more narrow. Let's try some examples. So let's suppose a population has a mean of 30 and a variance of 25. If a sample size of 100 is drawn from the population, what is the probability that the sample mean will be larger than 31? Okay, so the first thing that we need to do is we're recognizing that we are talking about a sample. So a couple things we should do first. One, what is it asking me to find? Find the probability. Okay, so probability is a keyword because that tells me I am calculating a probability and I need to use our guru and my probability calculator. So I want to make these keywords stand out. Here we go. Probability tells me go into our guru and get my continuous probability calculator ready. Okay. Then I take a look at, now that I know it's a probability, I need to know whether this is a probability of an individual or a group. And I see here, we're talking about a group of 100. So I know that I need a standard error. So here it tells me that I have a mean of 30 and a variance of 25. Now, when we're calculating probabilities, we don't use the variance, we use the standard deviation. So we have a couple calculations to do. We have to calculate the standard deviation, and then for that, we take and we calculate the standard error. So we have the variance being 25. And note the difference in the symbol. To go from variance to standard deviation, we take the square root of the variance. So I get 5 as the standard deviation if I was to take the probability of an individual, one person, being larger than 31. But since I want the average of 100 people being larger than 31, I need to calculate the standard error, which is sigma over the square root of n. So I get 5 divided by the square root of the sample size, which is 100. Square root of 100 is 10. 5 divided by 10 is 0.5. Okay, so this is my new standard error that I'm going to use in our guru. So we come over here and I'm typing in my mean of 30 and my standard deviation of 0.5. I am calculating a probability. So remember, this means I know some values and I want the probability. This one means you have the area under the curve, the probability, and you're actually trying to find the data values. This last translation, larger than 31, is how I'm going to identify whether I am a less than or greater than sign, and larger than translates as above 31. Remember, we don't need equal signs anymore. We don't need to care about strictly greater than or equal to, because in the continuous world, greater than 31 means 31.000000000000001, which is infinitely close to 31. Hit our little eyeball, and we see that it is a 2.28% chance of an average of 100 being larger than 31. Okay, so here we calculated and we found the probability. So the distribution doesn't look a whole lot different, but it should be more narrow, more normal. This isn't drawn to scale that well. Notice that when we were talking about in distribution of x values, our center is at 30. If we wanted to translate this into z-scores, we could do that, but we actually don't have to anymore. Our guru can calculate things, as you can see, as long as you change the mean and the standard error, it will calculate those probabilities. Let's try another one. The figure shows the mean distances traveled by drivers each day. You randomly select 50 drivers, ages 16 to 19. What is the probability that the mean distance traveled each day is between 19.4 and 22.5 miles? Okay, keyword in this word problem, and again, it's really helpful to identify keywords, especially when you are taking an exam with mixed questions. You need to know, what are you doing? So probability, I get my probability calculator open. I don't need to clear it or anything, but I can if I want to. So let's delete the calculation, it clears it out. But I still need to type over this stuff anyway. Oh, there we go. And start a new one and it resets. So we know we're taking a probability. I then want to look for, am I taking a probability of one individual driver or group? And this makes it clear that we are looking at a sample size of 50. And we need to now recognize the mean of that group. So the mean for the targeted population, here's my target population, 16 to 19-year-olds. I look at the graphic and I see that the mean is 20.7 miles. So I am going to type that in, 20.7 miles. And then the standard deviation, I know needs to be a standard error calculation. They tell me the standard deviation is 6.5. So I need to calculate 6.5 divided by, so I'm putting this in my calculator, 6.5 divided by the square root of the sample size, which is 50. That gives me a standard deviation of 0.91923881155, and it keeps going. Now, be careful. We are rounding and not using an exact number, so you should use more decimal places than less in order for your 4 decimal place probability to not be affected. So I threw in, let's see, 7 decimal places. That's where I stopped. I think that should be fine. And we want the probability between 2 values. So I'm going to select between. And I'm going to say that the value on the left side is 19.4. And the value on the right side is 22.5. And we'll calculate the probability of that happening. And it comes out to be 0.89624, or 89.62% chance that the average of 50 drivers ages 16 to 19 will have a mean distance traveled each day between 19.4 and 22.5 miles. Okay, next example. Some college students use credit cards to pay for school-related expenses. For this population, the amount paid is normally distributed with a mean of $1,615 and a standard deviation of 550. Question 1, what is the probability, already picking up on that keyword, that a randomly selected college student, no S, so that's a one individual, who uses a credit card to pay for school-related expenses paid less than $1,400. Okay, this does not require a standard error because I am only calculating this probability on a single student. So I do need to verify some things. I need to verify that the samples that this data was taken from, let's see. Okay, this is population mean and standard deviation, and it also tells me that the population is normally distributed. So I'm good to go for calculating this probability. I am going to put in the mean, which is 1615, and the standard deviation, not standard error, because it's only one individual, so I do not need to calculate a group standard error. And it's asking me about less than 1400. So that's a below calculation and below 1400. Okay, so there is about a 35% chance that a student would use less than $1,400 to pay for school-related expenses on their card. Now, question 2 says you randomly select 25 college students. So now we do have a group of students and we want to know the probability again. So I stick with my probability calculator and they want to know about less than 1,400, but this time for a group of 25. So the only change we need to make is we need to take this 550 and divide it by the square root of the sample size. And the sample size is 25. Now, the reason why this works, 25 is less than 30. That is not a sufficient sample size, but it works because, again, it's stated it's from a normally distributed population, so we're okay with smaller sample sizes. So 550 divided by the square root of 25 comes out to 110 for our standard error. And calculating the same probability, but this time for an average of 25 students, we see that the probability of them spending less than 1,400 is a greatly lower, only 2.5% chance versus the 35% chance of a single student. But let's think about that. If we're considering only one student's spending habits, the probability is going to be higher that we can control how much they spend. But when we're talking about averaging 25 completely individual college students and their spending habits, it really only takes 1 or 2 students to buy a computer that semester to screw the average of spending, and therefore making it a lot less probable. Now let's talk about calculating the error of our calculations. So consider the same scenario as in example 9.3.1, except that the mean is unknown. So which example was that? 9.3.1 was this one. Supposing a population mean of 30 and a variance of 25, sampling 100 at a time and a probability of larger than 31. They're saying, now let's say that we don't know this mean. This mean of 30, it's unknown. So if the sample mean is used as an estimate of the population mean, what is the probability that the sample mean will be in error by at most 1 unit from the true mean? So we're saying if we don't know the population average and we use the sample average, how can we account for the potential error of how far off that sample average is? So for example, if I was talking about grades on an exam and I didn't know the population average for my Stats 1 exam. So I used this semester's average of students taking that one exam. Let's say it came out to 80, an 80 on the exam. But when I did actually see the population average, let's say I actually did get it at some point, and the population average was 75. So I'm trying to figure out, what we're doing right now is we are trying to estimate what that error margin is by using a much less accurate average calculation. So Okay, so we want to calculate the probability that the sample mean will be in error by at most 1 unit from the true mean. So if we were talking about my grades problem, then we are trying to calculate the probability that the actual average is between 79 and 81, which wouldn't have been the case if it was 75. The concept of using a statistic to estimate a population parameter introduces the concept of a sampling error. In general, the sampling error is the difference between the sample statistic and the parameter which describes the population that we're estimating. So in this problem at hand, the error given is the difference between mu, the population average, and x bar, the sample average, since we will be using x bar to estimate the mu. However, we are just as interested in negative errors as we are positive ones. Thus, to satisfy the condition that an error of less than 1 unit has been made, the condition can be used with absolute values. What is the probability of that error? Okay, well, the probability that the difference between the population and the sample calculations being less than 1 unit away is equal to looking at the population average -1 and population average +1 and seeing if this sample calculation is between. So again, if my sample average on the test was 80, I am trying to hope that it's sandwiched between 79 and 81. But since my population mean I'm saying is 75, what I'm really saying is 80 between 74 and 76, which after the calculating, we would find out that no, it's not. Following these steps, really, we just need to care about this one right here. You can start here in the future, where you take -1 and put it over the standard error using the sample mean and 1 over the standard error. And then for this example, remember our standard error was 0.5. We calculated that. So if we put 0.5 in, we get a z-score of -2 and 2. And we're saying that what's the probability that the z-score representing the sample mean is between -2 and 2. And we can calculate that probability here, the probability between two values. So we are talking about z-scores, so you would change this back to 0 and 1 for the standard normal curve. And we want to be between -2 and 2. By the empirical rule, I know that should be close to 95%. So this one's a little less needing to be calculated because the empirical rule tells me it's 95%. And that's exactly what happens here. We get that 95%. So there's a 95% chance that, according to this example, the sample mean will be within 1 unit of the population mean. Okay. And that concludes our discussion about sampling distributions and the central limit theorem.